And we are good to go. All right, hello everyone. Welcome to the new space. Today we're kind of just gonna go through, and it's gonna be a chill day. I had a very interesting Reddit conversation with someone teaching me a little bit about how LSTMs work. He also said that Wikipedia has pretty good resources, which I took a look, and Wikipedia, I don't know why, but when I opened it before, I kind of just dismissed it and I went, nah, this is too much. But it's actually fairly straightforward, and I actually understand it. Now maybe that's because that's after I went through his the website that he recommended I look through and I read through, and I'll post this. I'll post a link to this website in the description because it's a very, very, very good resource, I think, at least. So it's giving me an idea of how LSTMs work. I know how forward prop for LSTMs work according to these formulas. So whether or not it's going to be as easy as I think it is, that's a different story. So the plan for today is learn about back prop, and then just map out how the forward pass and the back prop will work. And then tomorrow what we'll do is we'll actually go ahead and we'll build it in Excel. But for now, let's just go through and let's just, I might need to zoom in just a little bit. But for now, let's just go through and let's start understanding how LSTMs work. I know how forward prop works. So once again, thanks to this amazing article that explains everything much better than the code I was kind of cracking my head trying to understand does. What this resource also does is that it helps me understand these. I think that's why I now understand the formulas in Wikipedia, because of this blogging way kind of breaks things down. So yeah, so I mean, again, maybe more so just for me, just to kind of see if I understand LSTMs. But again, an LSTM is pretty much just like an RNN in that it has a recurrent it's a version of a recurrent neural network where the output of one layer feeds back into the input for the next time step, and so it allows you to take a look at sequential data. It's usually it's mainly just used for like time steps, or the different steps are usually just called time steps. So for LSTM, it's pretty much the same thing, except that it incorporates a memory called the cell state. So that cell state pretty much just passes along, and it gets passed to all other from this current time step will manipulate the cell state. The next time step will manipulate the time step as well. Yada yada yada. So the cell state is essentially just the memory for LSTMs. And so when we go through, there are a few things that get added. So the first one is a forget gate. So this forget gate here, I mean, look at that. Look how nice this formula is. This is a nice formula. It's really easy to follow along and properly understand what's going on. So the forget gate, essentially, just as its name hints towards, the cell state is over here, and so the forget gate just controls what gets removed from that cell state. Again, cell state's the memory, right? So that's that. And then here what we have is we have an input gate. So an input gate. So this is actually pretty interesting here. So what we're doing is we are saying, okay, this input gate here. What it does is that it acts as like So let me just think about it for a second. So in the next time step, so in this current time step, what we're doing is, so in this current time step, see, we have the current input and we also have the output from the previous time step. And so once the two of them come together and we manipulate them for the current time step, we then have a choice. The choice is, do we keep that in the cell state or not? And so that's what this part is doing. This part determines whether or not we actually go ahead and we keep it in the cell state. Whereas this part over here just determines, what's the value. So again, it's just a combination of this current time step plus the previous time step. And so you just combine them and you just manipulate them. So that's what this is doing here. And then this over here just determines whether or not we keep it in memory or we just leave it alone and we discard it. So that's what that does. Again, nice, really easy to follow along formulas here. And then over here, what we're doing is, so we have the values from the forget gate. We have the values from both the new or the yeah, so we have the values from the forget gate. We have the values. So we have FT. Remember, again, FT was our forget gate. We have CT. Remember, again, CT was just what we discussed over here, which is the current time step plus the previous time steps output that get manipulated together. And so this is kind of like a candidate for what the new cell state should be, but we don't want to overwrite the cell state completely. And so that's why we have I, which just indicates whether or not we should actually go ahead and input that value into the cell state. And so that's what we're doing here, is we're just combining all of them together to give us our new cell state for this current time period. And then we pass that cell state, we pass it to the future, or to the next time step. So then finally what we do is then we finally get our outputs from this current time period. And so our output, so we get our output. So the output is the whatever we have or whatever we inputted to this time step again, plus what we had previous time step. And what we're doing is, so that's what we have over here, and that's OT. And then what we're doing is we're now combining it with the cell state, with the data we have in memory, and then that forms the new output for the current time step. So that's that. And then, you know, there's other variations of an LSTM. So there's one called the peephole, and the peephole essentially, so if you remember up here, these different gates, let me go back all the way up here. These different gates, so the forget gate, the input gate, the new cell state candidate, as I like to call it, and then the output gate. What you realize is that they're all influencing the cell state, but none of them really know what's going on in the cell state. So that's exactly what peephole is. So peephole, it gives them access to to be able to read what's in the cell state. And so then they just use that to determine what to do next, to determine whether to forget, to determine whether or not I want to input, and to determine what should be outputted from the current in the current time step. And so that I understand. I don't fully understand this yet, but I'll take a look at it and I'll try to make sure I understand it later. Oh, okay, never mind. Okay, actually, this is pretty simple. Basically, what this is saying is that, you know, again, there's forget and then there's input. And so in the previous vanilla LSTM, you do forget and then you do input. And so basically what this is saying is, well, I mean, you only need to input if you decide to forget something, right? So if you forget something, let's just replace it with an input. Let's just replace it with something else, and so therefore you have to input. So that's just what this is saying. And vice versa, if you want to input for something, we have to forget something, and so that's how it works. That's why. And so it makes sense. It's called, what's it called? I don't know. It just says we're using coupled forget and input gates. That makes sense. And so now that we have kind of the broad overview of what an LSTM is, there's something called a GRU, and stands for gated recurrent unit, for like the one person who's interested. And essentially what it does is that it just combines the forget and input gates into one singular update gate, and that just has the effect of just making the math simple, and there are fewer weights to calculate, and so it takes less resources to run and update and yada yada yada. So that's kind of the effect. So it's just more efficient, right? And that's kind of the benefit of it. And then this very nice article kind of rounds off by just saying, you know, so there are more versions of LSTMs. Are there ones that are better than the others? Which is a question I had while reading through, saying, I mean, people have done research. Not necessarily. They're all, the performance for all of them are about the same, but the GRU is gaining popularity again just because it just has the one singular gate, and so it's just faster, easier to train. It's just more efficient because there are fewer parameters to train through. So that's that. And then if we like, so I again, these formulas are quite simple to follow, but for me personally, I do prefer the formulas on Wikipedia. And the only reason why I prefer them is because I think most of the industry uses this notation. Me personally, I kind of just prefer the Wikipedia notation. And so the one difference you'll see is that, you know, here we have the singular weight parameter, and we're multiplying it by the previous time steps output and the current time steps input. Whereas here in Wikipedia, they kind of broke it out into two separate matrices or two separate parameters. So you have your weights for the current time step, and then you have your weight parameters for the previous output for the previous time step, and you have your bias. And so, especially when we're building it out in Excel, that I think it will just be a lot easier if we have two separate parameters. that we can keep an eye on and we can visualize. So that's forward pass for LSTMs. Makes sense. It sounds simple in theory. I think it's a lot better now that I finally understand what's going on under the hood. Do you want to attempt going through this code again? I really don't like this code. This code has pissed me off so many times. But before we go back and before we try to take a look at code again, the one thing I do need to do is I need to learn a little bit more about backprop. So let me learn about that. Yeah, so I guess one thing I forgot to mention, so the reason why we use or RNNs, LSTMs are better than RNNs is because LSTMs, again, that cell state persists into the future, and so that's giving it memory, whereas RNNs, because all it's kind of looking is just one time step in the past, it's more of a short-term memory type of thing, and so that memory fades away the further and further into the future it gets, and so it kind of forgets what's happened maybe like 2-3 time steps in the past. Again, I think there are versions of RNNs where you can build where that persists for longer, but not as far into the future like LSTMs can. I need to do some more research on grooves to better understand them. Because I mean, like, I understand the formulas, I understand kind of the theory behind the formulas and things like that, but I just don't understand like what does ZT mean? What does RT mean? And also it looks like the hidden state is now, sorry, it looks like the cell state, which was in the previous versions of LSTMs, and it now gets turned into a hidden state. So yeah, I mean, I just have to better understand exactly what these things are rather than just kind of the fuzzy conceptual understanding, theoretical understanding that I have right now. But that will come later. I guess I'm learning more about grooves right now. Yeah, no, I stumbled upon a really great article that explains what grooves are, and so I'm just combining that with this amazing article from, I'm not even going to pronounce the name, Cola. I just pronounced the name, never mind. And so, but essentially, you know, this Z, it looks like it's an update gate, and then this is a reset gate, and these are the new candidate hidden state values, and then this actually updates the hidden state. Now, the one thing I am confused about is if this is an update gate, then why are we doing 1 minus it in the next time step? Because let's say, so if update has a value of 1, meaning we want to update it, oh, that's pretty smart, I see. It's actually really, really smart. So if we do want to update something, then this is 1 minus 1, which is 0, times the previous value, which now is zeroed out. And then what we're doing is we're multiplying the current or the update, or sorry, yeah, we're multiplying by 1, which is the update value, by the candidate, the new hidden layer value that we want to keep. That's freaking smart. I'm feeling confident until it's time to actually put this in code, but I'm feeling very, very confident about this right now. So we have ZT, which is our update. Sorry, yeah, we have ZT, which is our update, and so we have sigmoid, and we multiply that by the previous hidden and current x, and that gives us basically gives us a value between 0 and 1 that indicates whether or not we want to keep that value. Sorry, yeah, 0 and 1 which indicates whether or not we want to forget the value or, you know, update the value, or if we want to keep it. So 0 and 1. Okay, back up. So ZT gives us a value of 0 and 1. 1 is for if we actually do want to go ahead and forget the value, and 0 is whether or not we don't want to. Okay, so let's step back one more time. So we have ZT. ZT gives us a value between 0 and 1. ZT is an update gate. Wow, So we have ZT, which is an update gate, and it gives us an output of 0 and 1. 1 is whether or not we actually do want to go ahead and we want to update that value, and 0 is no, we don't want to update that value. We want to keep the old value. And then anything in between is just, we kind of want to keep it. We kind of, you know, wherever it lies on the spectrum. That's that. So I understand that. The reset, though, I kind of need to do a little more reading on what the hell the reset gate is. guess the reset is kind of like the forget gate from the previous LSTM. It's just for the future, do we want to keep the hidden time step as is, or do we want to reset it completely? Do you want to reset parts of it? And so again, because you're pointing it through a sigmoid, you're getting a value of between 0 and 1. 1 for the reset gate, do we want to reset completely? 0, we don't want to reset at all. And so we want to keep the values from the previous time step. Pretty interesting. Yeah, and so then just as before, what we did with the candidate cells, or the candidate values, so the potential new values for the state set, for the cell state for the LSTM, you have candidate values for the hidden state as well. These get passed through, and we're multiplying our reset by previous time step. So again, if it's 1, that means we do want to go ahead and reset it. If it's 0, we don't want to reset it. Hold up. Does that make sense? What is 10h of 1 versus 10h of 0? So then, hold up. Hold the hell up. 10h of... Or maybe I just have it. Maybe it's just the other way around. It's quite... Yeah, I don't know why this is. So I guess it's just reset gate outputs a 0 or 1, but it's kind of inversed. So 1 means that we don't want to reset the value, and 0 means that we do want to reset it. And so just set the value to 0. Yeah, it's a little, I don't know, maybe it'll sink in, but that just means that the way I look at a reset gate versus the way you look at an update gate, they're a little different. Because the update, 1 means an update, 0 means don't update, but I guess reset, 1 means keep, then 0 means reset, so kind of mess me up. I'm definitely going to make a mistake like that. I'm definitely going to mix that up in the future. That's an interesting point, something I'll have to keep in mind. LSTMs, they prefer small weight initialization, and just like normal feed forward, they are affected. They are affected by different weight initialization. So that's just something I'm gonna have to keep in mind. So LSTMs are prone to overfitting, and it is difficult to apply dropout to LSTMs. Interesting. Is it difficult as in it doesn't work, or is it difficult as in it's difficult to actually apply LSTM to it? I actually really like this site. What is it? Geeks for Geeks? Hands down would recommend. This and Cola, hands down, would 100% recommend for anyone looking to learn more about LSTMs and how they work. Oh. I was just gonna say, because of backprop, so today, like right now for tic-tac-toe, all I just really want is just an LSTM. I think we can do GRU and like other versions of LSTMs and play around with them much later. I just want to like finish this tic-tac-toe game. And trying to implement, what was it called? The peephole thingamajigger, trying to implement GRU. Again, people, like different research has been done. It's not that, one version is necessarily better than the other. GRU is just much more efficient because there's less resources involved to train and run it. So, but, to implement them, I have to then go through and look at how backprop works for them, blah, 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 blah. Too much work. So I'm just going to stick with normal LSTM because I have a resource here that I can understand. So the hell is J? Where the hell did you come up with the J? Huh?
I have a resource here that I can understand, so.
What? Okay, I know what that is. I know what that is. I know what that is. I know what this is. Okay, wait, let me take a step back. Actually, let me see if I think this is a typo. I think this too is a typo. I don't find them anywhere else, but there are mention of WXG. So I think this is supposed to be I. Yeah, so WHI. Okay, that makes so much sense to me. And then this is supposed to be This is not supposed to be WG. This is supposed to be, oops. It's not supposed to be WG. This is supposed to be WHG. And that makes sense because there's values for it. Okay. Okay, so I'm not going crazy. Okay, I understand this. Okay, let's keep going. It scared me for a second. Why are you using the letter Z? I need to stop being so judgmental about people's code and how they decide to explain things. But it's just quite random. Why little G is Z? Whatever. Why do you do the... No. I'm gonna forget that. I could code the forward pass right now, and I'm so confident I would get it 125% correct. I'm so confident. But let's do back prop. Let me learn the back prop part of it as well. And then once that is learned, then we will run into Excel. And I guarantee you that if like there are no, I don't think there are any gaps in my understanding, but if there are truly no gaps in my understanding, I guarantee you this will take like half an hour, maybe even less to build. Like this is actually super simple when you have someone explain it properly versus not even talk about the other. That code gives me PTSD. Let's not talk about it. Shouldn't it be the inverse of tan? I hate when you find an error in something because then it makes you hesitant as to whether or not you could actually continue believing it. Should this be tan or the inverse of tan? Why do these brackets not have an ending? Implementing this is going to be a pain in the butt because I have to guess where the brackets go. The brackets go here. The brackets go. I think the brackets go here. So I think. I don't know though. I have no clue. Okay. Yeah, backprop is always filled with a whole bunch of calculus, which I somewhat understand. No, there's not really. I mean, I don't really get much value from reading all these formulas. So the value I get is trying to implement it in Excel. This guy doesn't just gives you the formulas, doesn't explain it. What the hell is this? What's this value? This guy doesn't. All he literally did was just post, like, just vomited it out. Formulas, and this is his whole post. Yeah, this is a waste of my time. I don't think this paper looks interesting, but it doesn't have what I'm looking for. Okay, so I think I still have a little bit more research to do for backprop. I could try implementing it, but it's probably going to be a disaster, like like the forward prop was last week. So I'll spend maybe a couple more days just doing some more research, better understanding how that works, and then let's say maybe Wednesday I summarize all my research and start actually trying to implement it in Excel. I'm not giving up on Excel. And then we should be good. So once it's implemented in Excel, then translated to Lua, we then, there is one more part or one more thing that I'll need to figure out. It's how to make a reinforced, so this is all supervised learning, right? Like you provide the LSTM, the inputs, and you also provided the outputs that you wanted to generate. With a game like tic-tac-toe though, it's not possible, right? I can't give it every single state and what it has to do at every single state, especially because different states, you know, like there are multiple things you can do, or there are multiple tactics or strategies in multiple different positions that you can play in. So it's not feasible to give it, it's not feasible to use supervised learning to play tic-tac-toe. So what I'll have to do is I'll have to figure out how to use LSTM in reinforcement learning, where it plays by itself and then it then trains its LSTM. It might actually be similar to how the DeepQ network worked, right? Where it just has a pool of memory, and then instead of using a vanilla neural network like we used in the, well, it's kind of vanilla mixed with like a little bit of Q-learning. But instead of using that structure or that architecture, maybe it's just you get the memory and then you pass it through an LSTM. I don't know, actually. I don't know. So I'll have to figure it out. But that is it for today. And I'll see you guys tomorrow. Oh, you want to know what would be a really, really cool idea, or like a really, really cool application of LSTMs? If you had a game where people had to like draw pictures, and then the neural network had to caption the picture that you drew, that'd be really interesting. That'd be very, very interesting. I'd love to see what the results of that would be. I'm definitely gonna do that. That's going to be that's on my that's on my never-ending to-do list. Or another one where people have to write stuff, and it has to, like, you write into the game has to figure out what it is you wrote. Or you can turn that into like a multiplayer game, right? Where you write, it's like kind of like broken telephone in a sense, right? Like you write something, the AI has to determine what you wrote, and then it sends it off to a friend, and then they have to, they just say, oh well, again, like broken telephone, is this what you wrote, or is this what your image was? So it's kind of like you AI helps to facilitate the game of either broken telephone, but in this case you're writing it down, or it's that game called Pictionary. Yeah, Pictionary. Oh, ho, ho. Yeah. Pictionary with Pictionary with an AI. I'm gonna write that down. I'm so fresh and I've had a lot of sleep and I've done no work, so I'm not burnt out at all. So I'm full of ideas today. What you could do is what's it called? There's that thing where it's like this, like X word means something in my language, and I think that's beautiful. And so I think it'd just be really cool if you use that and put a twist on it, and had the AI translate your like a word from English or whatever to person's native language, and see just whether or not it gets it correct.